Hi, my name is Nathan Mikhail, and I am presenting to you today with my teammates Andrew Rooney, Justin Diala, and Ramana Vasanthan. Our client is Dr. Stephen Knudsen, and we are the AI voice processing on an FPGA team. Our project was motivated by the desire to demonstrate machine learning-based audio noise suppression and keyword detection on a resource-limited, non-networked edge device. This is an area of interest because most ML audio filtering options are computationally expensive and require cloud-based resources which are not fit for applications with disadvantaged network interfaces. These applications could include noise suppression in military vehicles, helmets of soldiers or firefighters, or eliminating the loud hum of cooling solutions when communicating in large server rooms. Therefore, our goal was to find an ML algorithm that could capably suppress noise and accelerate that model on an FPGA, running the system in real time with latency less than about a quarter of a second. Lastly, we wanted an ML solution to detect keywords that could be run on an edge device accompanying the voice filtering solution as mentioned above. Our presentation will discuss the noise filtering ML model, software implementation, overall filter results, the keyword detection model, and we'll conclude with a live demo. Now I will talk about the ML model selection and the processes we went through to accelerate our chosen model and hardware. Initially, we started our research with a convolutional neural network. However, it was quickly discovered that due to massive resource needs from the CNN, it was not feasible for our project. We then shifted our focus towards a recurrent neural network, designed and trained by Mozilla. The RNN's recurrent connections give it the ability to model time sequences. This makes it an ideal architecture for audio processing. The model was presented in a pre-trained C-based format, which we used as our starting point for hardware implementation through Xilinx's high-level synthesis tools. After making architectural modifications, the model was able to be synthesized but used floating point arithmetic. This resulted in 213% lookup table utilization on our targeted ZU3EG device. Additionally, the floating point model had an end-to-end latency of 3.8 milliseconds at 300 MHz. This was all improved by using 2214 fixed point arithmetic, and along with other optimizations, yielded only 67% lookup table utilization and 0.25 milliseconds of latency. Future work related to the voice filtering model includes additional resource optimization and further model training. A more detailed analysis and exploration of HLS capabilities or neural network optimization techniques, such as pruning, may result in less hardware resource utilization and latency decreases. Lastly, the quality of the neural network's training, and hence performance, may be increased through more detailed training. Andrew will now talk about the software implementation of our project.
Hi, my name is Andrew, and I'm going to talk about the software that we're using in our noise filtering system. So first off, why are we using software? And it's because of the non-trivial data pre-processing that's required for our neural net. The pre-processing was much easier to do in software rather than design custom logic for our first iteration. Our software uses the free RTOS kernel and runs on the Cortex-A53 of the multiprocessor system on a chip. Our software is responsible for buffering data at the input and output of the filtering system, initiating and responding to DMA transfers to and from the audio codec. It does the pre and post processing of the data and initiates inference on the RNN model. So the software posed some challenges when we were first trying to get the system to run in real time. Since the RNN operates on 10 millisecond buffers, we needed the processing time to be less than 10 milliseconds to support real-time throughput. And when we first ran our software, it was taking about 100 milliseconds per 10 millisecond buffer. That amount of time was dominated by the pre-processing, which was doing a lot of floating point operations. We were able to get a tenfold speed up just by letting the compiler optimize the code for our processor, which got us just over 10 milliseconds. It wasn't quite good enough to get smooth audio, however. And then we were able to get another tenfold speed up just by making sure that the DRAM cache was disabled only in the lines where DMA transfers were taking place. So with these changes, we got the system to do the data processing in just under 1 millisecond, and we are finally able to run the system in real time. So now for some numbers. All told, our data processing takes 0.7 milliseconds, and you can see the breakdown there. The total latency of the audio filtering is 27 milliseconds, which is dominated by the data buffering, which helps to smooth out the sound. We found that buffering and operating on 20 milliseconds of data at a time and running the scheduler at 900 Hz gave us pretty smooth audio. But there are still some artifacts from the software processing that we were unable to debug, and we'll see that in the demo. So the future work for the software would be to scrap it and develop FPGA logic to do the audio pre- and post-processing instead. This would reduce the overall system complexity and would likely give us smoother audio. So with everything running smoothly in our system, we found that it was quite capable of filtering white noise and babble noise. In our tests with audio samples with white noise in the background, we found that the signal-to-noise ratio was improved by 45 decibels. And in samples with babble noise in the background, the signal-to-noise ratio was improved by 30 decibels. And we can see that in these images down at the bottom here. Noise in the second image is completely filtered out and we're left with the original speaker. And you'll see this in the demo that the system performed quite well. However, the system did not perform very well with non-stationary noise. For instance, in our tests with a dog barking in the background, we actually saw a minor decrease in the signal-to-noise ratio, about 0.4 decibels. So in the future, we would look at further training of the model to help to improve the performance with non-stationary noise, since that's an important part of our user stories. Now I'll pass it off to Justin to talk about the keyword detection model.
Hi, I'm Justin, and I'll be talking about the voice detection aspect of our system. Our voice detection model is made through Teachable Machine. Teachable Machine is an online machine learning model trainer that takes an audio of the background noise and the keywords that the user wants to be detected. From that, Teachable Machine trains a machine learning model to detect the keywords from the background noise. Teachable Machine models are natively using TensorFlow.js. For our applications, we want it to be offline only, so we have to host the TensorFlow libraries and models in a simple Python server. Then, a simple user interface was made that uses TensorFlow.js and WebGL. The user interface was then made through Node and Parcel. TensorFlow.js enables us to use WebGL to leverage the GPU so that we can process audio input into the model fast to meet real-time constraints. The downsides of this approach, while effective, is that it requires the use of a GPU, and the real-time aspect of the voice detection is severely limited by the GPU. In our earlier prototypes, we tried running the voice detection through a Raspberry Pi board, but since the Pi board did not have a powerful enough GPU and CPU, it failed to meet our real-time constraints. Now, Ramana will talk about the keyword detection's future work.
Hi, I'm Ramana. I'll be going over the future work that could be done with our keyword detection model. So one potential option that we were originally exploring was to use Petalinux on the A9 processor of the UltraScale MPSoC to control keyword detection. We were able to run Python scripts on Petalinux with third-party libraries, so it would be a matter of converting the model file created by Teachable Machine to a Keras model using the already implemented TensorFlow function in Python. However, it would have taken more time than we had available to multiplex the audio output to the processor and test the Teachable Machine model conversion, which is why we instead opted to use the JavaScript implementation. An improvement that could be made in regards to latency would be to implement the Teachable Machine model fully on the FPGA. The HLS4ML Python library can convert TensorFlow and Keras models to synthesizable C code targeted towards FPGA implementations. This would help reduce the latency of keyword detection by taking away the overhead caused by an operating system, as well as by using custom logic versus a processor or GPU. Additional functionality could also be added to use the keywords to control the rest of the system, such as to toggle mute or to toggle the voice filtering system itself. Overall, we were successful in implementing an offline keyword detection model on a separate machine to take the filtered audio as an input and recognize keywords of our choice. The model has approximately 50 milliseconds of latency, which can further be improved on with our proposed future work. Now back to Andrew to give a short conclusion.
So overall, we successfully demonstrated a real-time noise filtering system that met the key requirements that were laid out by our client. We also demonstrated the operation of offline machine learning-based keyword detection. And in further design iterations, we would hope to refine our system to be more performant in the target scenarios by further training and some small design changes. Now we'll demo the system.